having some discussions about alpha, beta, and gamma decay, and we have discussed that these are the three most common type of radioactive emissions. We have discussed, we have some discussion about alpha, beta, and gamma decay. Let, let's have some practical uh, examples. For example, we have a parent nuclei americium with atomic mass 241. So when the americium undergoes alpha decay, so it's converted into a neptunium with the atomic mass 237. So alpha particle of mass 4 mu is being emitted. So just like that, we have a tritium nucleus, and a tritium nucleus is converted into helium-3 nucleus when it undergo beta decay. That is, uh, one neutron from the tritium nucleus is converting into a proton. So the nucleus from the tritium, where beta decay is converted into helium-3. Similarly, we have a helium-3 nucleus that is in the excited state. So it emits gamma decay. We say that it undergoes gamma decay, that this particular nucleus emits gamma radiation. So after that, it comes into the stable nucleus, that is again into helium-3. That is what we mean to say that the type of the atoms do not change during the gamma decay, or we can easily say that in gamma decay, the atoms only come to the stable state by emitting a gamma rays photon. So let's come toward the alpha particle again. Uh, let's have some brief definitions for the alpha particle. So an alpha particle is identical to that of a helium nucleus. How is that? So like you know that uh, when we are saying that the alpha particle is similar to a helium nucleus, we mean that just like a helium nucleus, it contains two protons and two neutrons. So how the alpha decay occurs? So let's give us an example. Like we have an unstable atom that is being denoted in these equations by X with the subscript and superscript, the subscript Z and superscript A. You know that Z it represents the atomic number, while the superscript A represents the mass number. So with alpha decay, when alpha decay occurs, so we have a more stable atoms that we represent by Y, and we have here in the subscript we have Z minus 2. That is, we mean to say that the atomic number is reduced by 2, and the superscript we have that A minus 4, which means that the stable nucleus that we have after the alpha decay, in that particular situation, the mass number is reduced by 4. Plus, we have the alpha particle, which we denote by the helium nucleus, that is atomic number 2, and atomic mass equal to 4. So these are the typical equations we write for the alpha decay, journal equations. So what is the practical examples for alpha decay? So let's have, for example, we have a radium atoms the radiums have an atomic number 88 and atomic mass equal to 226. So when alpha decay occur from the radiums, so we have what? During the alpha decay, the radium atom is converted into radon where the atomic mass equal to 86 and the atomic mass 222. is the practical example of the alpha decay. That is, when radium undergoes alpha decay, so it is converted into radon. Similarly, that looks another example. I mean, we have the same general equation of the alpha decay. So what happened in the practical example? That is, the radon with the atomic numbers 88 and atomic mass 226 is converted or is changed to radon with atomic mass 86 and atomic number 86 and atomic mass 222 with the uh, emission of alpha particles. So what happened with the radon? Again, we say that radon is also not a stable nucleus. So radon can further go the alpha decay. So what happens when radon undergoes further alpha decay? So it brings a daughter nuclei. Uh, so what happened with that? When radon undergoes alpha decay, so it produces polonium with the atomic number 84 and atomic mass 218. What it means? It means that radon by itself is not a stable nucleus. So after its half life, it again goes to alpha decay. So what it means that we start from uh, radium. From radium first we have radon, and then from the radon we have polonium. Uh, but again we say that we have another parent nucleus, and that parent nucleus after alpha decay is converted into thorium with the atomic mass 90, with the atomic number 90 and the atomic mass 230. So what is that parent nucleus? So the parent nucleus in this particular situation is uranium 234. So uranium 234 after alpha decay, it is converted into thorium with atomic numbers 90 and atomic mass 230. So thorium is also not a stable atom. It can also decay. It can also have the alpha decay. So after alpha decay, thorium is converted into another daughter nucleus. So the practical example for this situation is we have a thorium, and that thorium after alpha decay is converted into radium uh, with the atomic number 88 and atomic mass 226. So another example is uh, we can say that the alpha decay process continues until the unstable atoms do not get the full stability. That is, it should reach to a state where it cannot further decay. I mean, during the decay process, the atoms they're trying to reach to their stability point. So we should have an unstable nucleus, and that unstable nucleus should eventually goes to the lead, which is a bit stable nucleus by alpha decay. So what is that particular nucleus? Parent nucleus they decay to lead. So we have polonium with atomic mass 84, with atomic mass number 84 and atomic mass 218, which after alpha decay uh, gains the atomic state of lead, the atomic number 82 and the atomic mass 240. So this is the stable state that the element or the atom gets after alpha decay. So this is all we have for alpha decay. So in the next lectures, we will talk about